Here we go. In section 9.1, we're going to discuss sequences. Uh-oh. There we go. So, as far as the definition goes, a sequence is a function whose domain is the set of positive integers. So basically it takes the number 1 and it sends it to a specific number. And then it takes the number 2 and sends it to the specific number. And 3 sends it to this specific number, and so on and so forth. And those numbers are called the terms in the sequence. Now, it's there's a couple of different notations when you're dealing with sequences. A lot of times you'll see a sequence as an infinite list of numbers. So A1, A2, A3, and so on and so forth. AN is the number which the function sends the n to. So one of the ways you see sequences is an infinite list. Obviously, if the domain is a set of positive integers, this list goes on forever. So that's what I mean by infinite list. So again, we can take this sequence and we can write out terms in a list, but there's a couple of other ways we can write out a sequence as well. A lot of times we use this brackets a sub n or f of n. So what you do is you write in brackets the actual formula of the function. So for instance, well, we're going to look at this, but basically you write whatever formula the function is. So let's say a sequence sent 1 to 1 and 2 to 2 and 3 to 3. So that function would be a sub n is equal to n, or f of n is equal to n. All right. So one way you can write out a sequence is write it out as basically an arbitrary term. Another way you can list a sequence is to do it recursively. So what that means is that you say your first term is a specific number, and then every term that follows that, there's a pattern. Maybe you add 1 every time you increase the terms. Maybe you add 3 every time you increase from one term to the next. So that's what's called recursively defining your sequence. And this is defining your sequence as a function. We're going to look at a couple of examples of this in a second. So let's go ahead. Oh, this one's not very well. There we go. Let's go ahead and find the first 5 terms of these sequences that are listed by functions. So what you see here is what I call the function notation. N divided by n plus 1 in brackets. Now what that means, let's escape this for a second. What that means is that n divided by n plus 1 is the function, so you could write it this way, that gives you the nth term in the sequence. You could also have written it as a sub n is equal to n over n plus 1. So the nth term is n over n plus 1. Now if we were to list out a sequence, list out the first few terms of the sequence, all we have to do is start plugging in the numbers which are positive integers. So plug in 1 for n, that'll give you 1/2 as the first term. When you plug in 2 for n, you end up with 2/3 as the second term. When you plug in 3 for n, you end up with 3/4. And you can see the pattern here. 4/5, 4/5 is the fourth term, in the sequence, and then the fifth term in the sequence would be 5, 6. Now this pattern could go on forever if you wanted to. You could just keep listing terms out, but that's the idea. 1/2, 2/3, 3/4, 4/5, and 5/6. So why don't you go ahead and try to do that. Push pause on the video, list out the first 5 terms of these other 3 sequences. If you don't know this last one, that's perfectly all right. We'll take a look at that last one together at the end. In fact, we'll take a look at all of these. But I want you to try, push pause on the video, and list out the first 5 terms of those sequences. If you didn't push pause, I gave you a little bit of a break to push pause. Make sure you go ahead and do that because I'm going to give you the answers right now. So I'm not going to keep writing f of n or a sub n. We all now have seen this notation with the brackets, and so now we know what that means. So we're just going to go right into the sequence. When you plug in 1 for n, you get 2 plus -1, so you get 1 as your first term. When you plug in 2 for n, this -1 squared becomes a +1, so you end up with 3. When you plug in 3 for n, -1 to the 3rd power is just -1, so you get 2 plus -1. You get back at 1. When you plug in 4 for n, -1 to the 4th power is a +1, so you end up with a 3. And you can kind of see every odd power is going to result in the number 1. Every even power is going to result in the number 3. So the first, well, I did 6 terms there, but the first 5 terms go 1, 3, 1, 3, 1. And then you would just keep going back and forth between 1 and 3 on each of the terms. Okay? By the way, we say this part of the sequence, this -1 to the n, we're going to see that a lot moving forward. So that's going to come up, this -1, where it alternates between negative and positive. Later on in the chapter, specifically, we'll see that. Now the next, the next sequence we see is n squared over 2 to the n. This one's kind of interesting. I might go a little bit further here than just the first 5 terms so we can see a pattern. But when you plug in 1, you get 1 squared, that's 1. 2 to the 1st power is just 2. So you end up with 1/2 as the first term. When you plug in 2, you end up with 2 squared, that's 4, divided by, on bottom, also 2 squared, which is 4. When you plug in the number 3, 3 squared is 9. 2 to the 3rd power is 3, so you get 9 over 8. When you plug in 4, you get 4 squared, which is 16, over 2 to the 4th, which is also 16, so you get 16 over 16. And then you plug in 5, you end up with 25 over 32. If you plug in 6, you end up with 36 over 64. And you could keep going on that pattern if you'd like. Go another one, 49 when you plug in 7 over 2 to the 7th power, which is 128. And so here's what's happening. By the way, notice in the first couple of terms, it seems like the numerator is getting bigger. 1 goes then to 4, then to 9. Whereas the denominator goes from 2 to 4 to 8. And then all of a sudden, the denominator starts getting much, much bigger than the numerator goes. We're going to see this later on too in the chapter. This is kind of the difference between polynomial growth versus exponential growth. And we'll find out, as long as our base is greater than 1, then exponential growth is always going to, in the long run, grow faster than polynomial type growth. All right, this is kind of something that shows you that. Now, the last sequence that we're asked to evaluate is n factorial. Now, this might not be something that you've seen. Maybe it is something you've seen, but let me just tell you what this factorial does when we're dealing with positive integers. When we're dealing with positive integers like 1 factorial is simply 1. 2 factorial, well, what this factorial does is say, take this number here, which is 2. Again, this is factorial with positive integers. And then multiply it. Let me get a better multiplication symbol here. I don't want to use the one there. That's better. Times every positive integer down till you get to 1. So sorry about that. Let me restate that. What this factorial symbol says. Let's take 3 factorial for instance. 3 factorial says start with 3, multiply times 2, then multiply times 1. So when we have a positive integer onto a factorial symbol, we have to start with that positive integer and then multiply every single number until every positive integer that's less than, in this case 3, until you get to 1. So 4 factorial is 4 times 3 times 2 times 1. And then 5 factorial is obviously 5 times 4 times 3 times 2 times 1. By the way, notice what we're doing each time. We're just adding a multiplication by the next number. So we've multiplied times 1, then 1 times 2, then that times 3, then that times 4. Basically, 5 factorial is just 5 multiplied times 4 factorial, if you think about it that way. Right? 5 times 4 times 3 times 2 times 1. Okay? And by the way, order of operations, you do the factorial symbol before you multiply the 5 times the 4. Okay? So when you see 5 times 4 factorial, do the 4 factorial piece first. Do the factorial piece first, and then multiply by 5. Order of operations of factorial. Factorial is in the same category as exponential when you do orders of operations. All right, so all that being said, here you see the first 5 terms. I'm going to list them out. The first term is 1. The second term, when you multiply 2 times 1, you get 2. The third term is 3 times 2 times 1, you get 6. When you take 4 times 3 times 2 times 1, you get 24. When you multiply that times 5, you end up with 120. By the way, you can see this pattern and what's happening. Times 2, times 3, times 4, times 5. The next one will be times 6. If you wanted to go out that far, that's 720. Again, I'm not going to knock you for going out further than we ask, but this one asked for at least 5 terms. We've given 6. No big deal. All right, so that's the idea of these sequences written in terms of functions. Now we can also do the same thing. We can list out terms of the sequences when we have our functions or our sequences defined recursively too. So if we look at this first one, a1 is equal to 2, and then an is 2 times a n minus 1. By the way, n minus 1 is the term right, a n minus 1 is the term right before a n. So what that means is if you're looking for a2, you multiply 2 times a1. Hopefully that makes sense when you do that. So let's list out the first. Let's look at this sequence to begin with, this first sequence. All right, so this first sequence, first term is 2. Every next terms, to go from 1 to the next, you multiply by 2. So first term is 2. The second term is going to be, again, if you think about this, if n equals 2, let me just kind of off to the side write this. I think most of you get it already. But if n is equal to 2, then a2 has to be 2 multiplied times a1. So 2 times the first term is 4. And then in a similar vein, a3 has to be 2 multiplied times the term before it. So we go from 4, multiply that by 2, you get an 8. Then multiply that by 2, you get a 16. Multiply that by 2, you get a 32. Multiply that times 2, you get a 64. Multiply that times 2, you get a 128. I actually can stop there because it just asked me for the first 6 terms. So those are the first 6 terms of this recursively defined sequence. Now, one thing you may notice is that this sequence here is very similar to a sequence we saw earlier that was defined by a function. Well, I shouldn't say it was very similar to the sequence, but it was very similar to the denominator in this sequence. We go 2, 4, 8, 16, 32, 64, 128. Notice that's just 2 to the n. So this recursively defined sequence that we just wrote actually could be written as what I'll call a function sequence as just 2 to the nth power. Okay, and that's the way a lot of these go. In fact, there's a theorem when you get into higher level mathematics that says any sequence that can be defined recursively can also be written as a function. So there you go. And not that that's something that we're going to look at in this class, but that is something. Even harder to define sequences like this one can be written as functions, although they're not as easily done. So this is a sequence that we're going to look at, kind of a interesting and famous sequence. It starts out by giving me not just the first term, but the first 2 terms. So it gives me that the first term is 1 and also that the second term is 1. And then it says an is a sum of the term before it and the term before that. So what we would say is that let me just write this, a3 would be a sum of the second term. If I plug a 3 in there, it's the first term. So a3 is a sum, 1 plus 1. a4 would be a sum of a3 plus a2. So 1 plus 2 is 3. Now at this point it looks like this is growing really slowly, but it turns out when we start growing, 2 plus 3 is 5, 3 plus 5 is 8. When you get out to a few terms, this starts growing really, really fast. 5 plus 8 is 13. 13 plus 8 is 21. 21 plus 13 is 34. And you can see it's starting to take off a little bit. 55 would be the next term, and so on and so forth. And yes, this can be written as a function. It turns out it's a really complicated function, and that function involves it involves a weird ratio, specifically, whoops, excuse me, the ratio of 1 plus the square root of 5, I believe, over 2. And if you do 1 plus the square root of 5 divided by 2, you get about 1.618. So the function involves that. I'm not saying this is the function. I'm saying it involves this term. And this term is actually the golden ratio, if you've ever heard of that. So when you write this function out in terms of a function with respect to n, this golden ratio appears. And this sequence here is actually known as the Fibonacci sequence. So the Fibonacci sequence is this sequence. And when you write the term as a function, it involves this number, which is the golden ratio. So the Fibonacci sequence is a famous mathematical sequence. It projects growth in the natural world in some instances. And then that Fibonacci number, this is golden ratio, also sometimes called the Fibonacci number. That also is a number that shows up in nature quite a lot, and in art and things like that. All right, so we've listed out some of the first terms of the sequences. We're going to, right now, I'm going to adjust this just slightly, do the reverse. So now let's assume we have the first few terms of a sequence, and we want to write out the function that gives us the sequence. 2, 5, 8, 11 is the first sequence, and then 5, 10, 20, 40 is the second sequence. I want you to go ahead and try to come up with the terms of the sequence. You have the terms of the sequence. Use the terms of the sequence to come up with the function of the sequence, right? An arbitrary value for the nth term. Go ahead and push pause on the video and do that. In about 5 seconds, I'll give you the answer. All right, so let's take a look at these sequences. First one, 2, 5, 8, 11. Now what I do is I look at how these progress, and hopefully you see that what's happening here is that each subsequent term is being increased by 3. Well, we know how to deal with that. When you increase by 3 over and over and over and over again, that's like dealing with a 3n of some sorts, right? Each time you increase n by 1, the term is going to be increased by 3. So we start with 3n, that's increasing by 3 each time. And then we have to start our look at the number 2. Now here's where it gets a little bit tricky. If our first term is defined as A1, in other words, we're plugging in 1, then all we have to do is make 3n plus or minus a number in order to get to 2. Obviously, in this case, we want to subtract 1. So 3n minus 1. And notice that, did I say a1? a1 is 2. I apologize there. So when I plug in 1 for n, let me write it that way. I need to make sure that I hit the number 2. So it's going to be 3n minus 1 so that I hit the number 2. I apologize for that. And that means that if a1 is my first term, then the sequence that I'm looking for is 3n minus 1. Hopefully that made sense. I kind of messed that up a little bit linguistically. Now, here's the issue with that. There are certain people, when you say from positive integers, certain people, instead of using the positive integers as their numbering system, will use non-negative integers as their numbering system. So certain people will start counting at 0 rather than 1. Now, if we want our first term to be called a0, then we're inputting a 0. So how do I get to a 2? Well, I have to add 2. All right. So if you're starting at your count at 0, then the actual sequence as a function will be 3n plus 2. Now, either of these are acceptable to me. You can start your count at 1. You can start your count at 0. Most people start their count at 1. But a lot of times, with specifically what we'll see later is called geometric sequences, the count often starts at 0. So that's the idea there. I'm okay again with either one, starting your count at 1 or starting your count at 0. All right, sometimes it's a little bit easier to start your count at 0. Other times it's a little bit easier to start your count at 1. So let's go to this one here. 5, 10, 20, 40. Notice that each time we're going to the next term, we're multiplying by 2. This would have been an easy one to do recursively, but let's do this using the function notation. So each time you're increasing, you are increase is multiplying by 2 every time. By the way, that means that somewhere in our sequence, we're going to end up with a repeated multiplication by 2. That's just 2 to the nth power. All right. Now, if you think about how this is going to go, again, if I want to start my count at 1, then I need to make sure that I'm taking this 2 to the nth, multiplying it times an appropriate number to get 5. Well, let me put it this way. 2 to the first multiplies by some number to get 5. And if you did that, the number you need to multiply by is 5/2. Hopefully that makes sense. So what would a sub n be? Well, the nth term would be 5/2 multiplied times 2 to the nth power. All right, and that would be the sequence. Again, we could start our count at 0. If I started my count at 0, a sub 0 would have to have been 5. And so I'm going to take 2 to the first power. Nope, not to the first power, to the 0th power. And I need to multiply times some constant out front to get 5. Well, it's pretty clear that that constant out front needs to be a 5 because 2 to the 0 is just the number 1. And so we end up with a sequence, the function notation of which is 5, whoops, let me write this down, 5 times 2 to the nth. You can see why starting at 0 there is kind of nice, because starting at 0, our coefficient here of 5 is in fact just our first term. So that one, when you have repeated multiplication, or in other words, when we know we're going to have exponents in our sequence, it's kind of nice to start at 0. Okay, by the way, this is called a geometric sequence because we're repeatedly multiplying each time. All right, I'm not going to explain a whole lot, but I want you to try to, on your own, push pause, and based on these first few terms of the sequence, go ahead and try to come up with the function. I am not going to go into as much detail, but I will give you the answers in about 5 seconds. So push pause on the video, try it yourself, and then come back and see if you got the right answers. All right, here's these sequences: 2, 8, 14, 20. Notice that each time we're adding 6, so my sequence can be defined as 6n minus 4 if we're starting our count at 1, or it could be defined as 6n plus 2 if you're starting your count at 0. All right. In this sequence here, what's happening on the top, 1 we should think of as the fraction 1 over 1, and then it should make sense that, we're dealing with numerators and denominators separately. In the numerator, what's happening is we're starting at 1, negative 1, 1, negative 1, so we're alternating back and forth between negative 1 and 1. If you remember how to do that, you either start at negative 1. Now, depending on whether I start my count at 1 or 1 or 0. If I start my count at 1, I need a positive number here on top. I need a positive 1. So the way to get that is to do n plus 1. That way when I plug in n equals 1, I get an even power on top. When I plug in n equals 2, I get an odd power on top. When I plug in n equals 3, I get an even power on top. When I plug in n equals 4, I get an odd power, and so on and so forth. So if I started at n, then my numerator would have to start at negative 1, positive 1, negative 1. So how we adjust that, we just put n plus 1. Now on the bottom, I screwed that up, we have 1, 4, 9, 16, 25. You should recognize those as the squares of various numbers. And again, if we're starting our count at 1, that's just n squared. All right, so my function is negative 1 to the n plus 1th power over n squared. That's what would happen if you started your count at 1. If you started your count at 0, it's going to be a little bit more difficult. I'm not even going to get into that one right now. Now this other sequence is kind of interesting. 2, 24, 720, 40,000, 320, 3,628,800, so on and so forth. And if you look jumps, ooh, these are big jumps. You could think maybe add 22 and then add almost 600, almost 700. That's a weird jumps adding. What happens if you multiply? Go from 2 to 24, that's a multiplication of 12. 24 to 720, that's a multiplication of 30. 12 is 3 times 4. 30 is 5 times 6. If you go 7 times 8 times 720, 720 times 7 times 8, you get 40,320. What I'm trying to get at is what these are. These have something to do with factorial, okay? Now what this is, 2 is actually just 2 factorial. 24 is actually 4 factorial. 720 is actually 6 factorial. So our sequence is actually 2 factorial, whoops, 4 factorial, 6 factorial. Sure enough, that next one is 8 factorial, and the next one is 10 factorial. And once you've seen it like that, it's pretty easy. It's the even powers factorial. So what you do is you take 2n factorial as the function that you're dealing with. By the way, notice that I am forced to put parentheses around the 2n. If you were to write 2n, whoops, let me do this again. If you were to write 2n factorial, what that is 2 multiplied times n factorial. So see the difference there? What we have is not 2n factorial, because you'd have to take the factorial times, or excuse me, the n factorial. You have to evaluate that first before multiplying. This time we're taking the 2n, multiplying that, and then taking the factorial of that. Again, hopefully that all makes sense. So that's the idea behind creating some of these sequences. Now, the other part of sequences that we're going to be very interested in is finding the limits of them. Now, a sequence is just a function. So if we know the expression of a function, a limit is the same as the limit of the function. Now, what do we mean by the limit of the function? We mean the limit of the function as n gets bigger and bigger and bigger. So when we talk about the limit of a sequence, we're really saying the limit as n goes to infinity of the function itself. Now we've done a lot of limits. Hopefully you've done a lot of these in Calc 1. We did a lot of the limits in the previous chapter as well when we integrated out towards infinity. So this should be a fairly familiar topic. And just like the previous chapter, we use the same language. We say converges. So the sequence converges if the limit of that sequence is a real number. And we say the sequence diverges if the limit doesn't exist, or if the limit is either plus or minus infinity. All right, we'll look at a few of these, both that converge and diverge. So let's take a look at the limits of the sequences that we dealt with before. We have n over n plus 1, 2 plus negative 1 to the nth power, n squared over 2 to the n, and then n factorial. Now we've dealt with each of these sequences before, so it should not be a crazy surprise. So let's take a look at this first one, n over n plus 1. Now we listed out the first few terms. I don't think I need to list those out again, but let's take a look at limits. So the limit as n goes to infinity. Let me write that. Where is the infinity I'm looking for? See if this does it. Whoops, excuse me. There we go. Limit as n goes to infinity of n divided by n plus 1. All right, that's what we're really looking at. So the limit of this sequence is the limit of this function as n goes to infinity. As n gets bigger and bigger and bigger, we've seen this in the last chapter. You could use L'Hopital's rule if you'd like, but we have the same growth on top, same growth on bottom, so we're going to look at the coefficients. We have 1 over 1, so the limit is 1. So what we say is that this sequence here converges to 1, all right? Because the limit of that sequence is 1. Now the next sequence that we had, I am going to list out the terms for. 2 plus negative 1 over n. Not over n, excuse me. 2 plus negative 1 to the nth power. Now remember, this one went back and forth between 1 and 3, 1 and 3, 1 and 3. And so if I were to take the limit of this sequence, let me borrow that so I don't have to type it in again. So take the limit of this sequence of 2 plus negative 1 to the nth power. Well, since it bounces back and forth between 1 and 3 all the time, this limit never converges to a real number. So this limit does not exist. And therefore, we would say that this sequence diverges. All right, and it diverges to no number in particular. It just bounces back and forth between 1 and 3. All right, let's take the next sequence. Now, this is what I was saying earlier about the terms. You say, well, which thing grows faster, the n squared or the 2 to the nth? Well, you'll see easily oh, I screwed that up, didn't I? There we go. There, that's better. That n squared over 2 to the nth, that even while these first few terms, it may seem like the n squared grows faster, the 2 to the nth grows faster as you get higher and higher and higher values of n. So it's almost like the top is standing still while the bottom is getting really, really big. Okay, and if the bottom is getting a really, really big number and the top is standing still, we saw in the last chapter that that thing is going to 0. These fractions are going to get smaller and smaller and smaller and smaller until they get super, super close to 0. So we say that this sequence converges to 0. All right, so there we go. And the last sequence here, n factorial, we've seen the factorial before. If I take limit of n factorial, clearly this thing is going to grow on forever. And so it is going to go to infinity. All right. So what we say is that the sequence n factorial diverges. Some people will say diverges to infinity. Other people will just say diverges. Either way is not a big deal to me. So there we go. By the way, there is something to be said about the growth of n factorial compared to the growth of 2 to the n compared to the growth of n squared. All right. I don't know if you know this, but I do want to mention this right now. Faster growth versus slower growth. Let's put the fastest growth on the left and the slower growth on the right. We'll go over this another time, but just of the functions that we've seen before, it turns out that if you're looking for the fastest growth of any type of a sequence, n factorial is really, really, really fast, okay? In fact, it's faster than even the exponential growth type thing with base bigger than 1. So like 2 to the n is a really fast growth, but it turns out n factorial is faster. You can kind of prove that to yourself if you like that, but factorial growth is a really faster growth than exponential growth. And then exponential, as I've said before, is faster than polynomial growth. So if you had something like n to the third power, or you can put a coefficient in front of it, 4n to the third power, that's a polynomial type growth. That's faster than any exponential. Now, I say polynomial in really loose terms because technically you could also put into that category any type of n to the, I don't know, 4/5 power. Dang it, I screwed that up. So 5 times n 4/5 power, right? Something like that. So it doesn't always have to be whole number exponents. So on your n, but some type of the powers of n. Instead of polynomial, but a lot of times I call this polynomial growth. So all of these grow, and as you take the limit, as n goes to infinity, all these go out to infinity. Again, exponential, as long as our base is bigger than 1, exponential growth is fast. As long as our powers are above 0, then powers of growth are fast. Slower growths that we're going to see are like natural log growths. That's a really slow growth. Or log base 10, that's a slow growth too. Okay, so fastest one that we've seen so far is n factorial. You can do some compounding of functions and make it even faster than factorial. But factorial is faster than exponential. Exponential is a faster growth than powers of n. Powers of n are a faster growth than log. All right? Hopefully that makes sense. If it doesn't, we're going to see that later. I just wanted to sort of mention that right now, that factorial growth is in fact faster growth than exponential. Now, there's a couple of theorems that the book gets into which are intended to make it easier to find limits. Most of the time, these theorems don't actually help a whole lot because we can find limits using techniques that we've seen previously in calculus. But I am going to mention what these theorems are saying and what they're trying to accomplish. So the first theorem is called the squeeze theorem. And it says if I have two sequences, we'll call them AN and CN, which converge to the same limit. And if I have what I'll call an in-between sequence, that after a certain point in time, these B's are all the nth term for the sequence B is in between the nth term for the sequence A and the nth term for the sequence C. So in other words, if B is always in between A and C after a while, then the B's have to have the same limit. All right, that's what's called the squeeze theorem. Now, you can do this by hand. The book does a couple of examples. Again, it's not worth actually going through because it's usually better to use other methods to find limits of sequences. We're not going to use this directly much, but let me give you kind of a crappy Microsoft Paint version of what this sequence is trying to do. All right. So let's say we have a sequence and we'll call it C and we'll call one A. It doesn't matter. Let's paint the C's in green, or excuse me, red. So I think the C's, they're the bigger ones. So let's say, remember the sequencers are functions. So when you graph them, you're going to be able to plug in the number 1 and you're going to get some sort of point. Hopefully that makes sense. Basically, this point is the point 1, comma, A1. Can't really draw it well, but does that make sense? So you plug in the number 1, you get the term A1. And then you're going to plug in the point 2, and you're going to get the term A2. So maybe you get something like this, and you get a pattern, and all of a sudden you start noticing that these dots are converging on a certain limit. And the way I'm drawing it, I'm going to have these dots converge towards the number 3. Now 3 is just arbitrary, it could be anything, but you see how this is going. It's flattening out towards 3. So the A's are going towards 3. And then we're going to have another sequence. Oh, you know what? I screwed that up. I apologize. That should have been the C's the way I have my theorem, but that doesn't matter. So we're going to have another sequence, and maybe this other sequence also has some dots. And once you know it, they are also converging towards the number 3. So the limit of one sequence is 3, and the limit of the other sequence is 3. Now, what my theorem says, what the squeeze theorem says, is that no matter where we start, if after a while I have a third sequence, and it always has to be between the blue and the red, then that third sequence is sort of, by way of force, forced to have the same limit, right? Basically, it's funneled in to that same limit. All right. And by the way, this is that fancy terminology about there exists an end so that there's in between. What that just means is that we could have started with, the first couple of dots being outside of one of the sequences, but after a while, it's always in between. So in this case, In this case, after the third dot, it's always in between. So that's the squeeze theorem. Okay, and again, I think I screwed up because A should have been my lower sequence, the blue, and C, I think, should have been my upper sequence, the red, with the way I've done this. Yeah, C should have been the upper sequence, A should have been the lower sequence. But that's the squeeze theorem. And so the squeeze theorem should make sense. I'm not going to test you on actually doing and applying the squeeze theorem because quite frankly, using the techniques that we saw in the last chapter of using L'Hopital's rule or using the techniques that we're kind of hinting at which function grows faster type techniques is what we're going to be focusing on throughout. There's also something called an absolute value theorem. This is misdone in the notes. I will post that. It basically says that if I ignore positive and negative signs and my sequence goes to 0, then the sequence itself has to go to 0. Okay, this is a corollary of the squeeze theorem. It's not that, again, important to what we're doing here. It's pretty self-explanatory. If it bounces back and forth, if your terms bounce back and forth between positive and negative, but they still look like they're going to 0, well, they're still going to 0. All right. Now here's our last theorem that the book gives us. It's called the bounded monotonic sequence theorem. Now let me explain what bounded and monotonic sequence means before I actually give you what the book says. So bounded simply means that there are numbers which you cannot go below and you cannot go above. So bounded sequence means that every term in the sequence is in between a low number and a high number. So for every term in the sequence, every term is bounded. It's always between a specific low and a specific high. Monotonic means that either you're always increasing or you're always decreasing. Now, when I say increasing, I could say increasing or staying the same. Decreasing means decreasing or staying the same. So bounded, you're always in between two values. Monotonic means it's always increasing or decreasing. And it turns out if your sequence is both bounded and monotonic, then it has to converge. Again, we don't use this whole thing a lot directly because it's easier just to take the limit of a function, but I do want to get you to understand what this is actually trying to do and why bounded monotonic sequences always have to converge. All right, so let me do that with, again, kind of a crappy paint drawing. So here we go. This is the best I can do without having to actually draw on the board. So let's say we're bounded. What that means is that I'm going to have, let's say, some y value that my sequence can't cross, which is above, and maybe some y value where my sequence can't cross, but is below. So we'll call my above bound, what is that? 1, 2, 3, 4, 5, 6, 7. So it's bounded above by the number 7 and bounded below by the number -2. There we go. I'm trying to draw with a cursor. It's all right. Let's go a little bit less. Now we're going to start a sequence, and I'm going to make it bounded between -2 and 7. And I'm also going to make sure it's monotonic. So I can only, let's say we can only increase. So I'll start with here. And then my second value maybe is here. My third value is here. My fourth value is here. Now, if I'm only allowed to increase, then I can never go back down. So I can only increase. And as I increase, I can't pass this number 7. So as I increase, I can only increase or sort of level out. Maybe we go this way, maybe we go here. So I have to increase, and eventually I have to start leveling out because I can't pass 7. Now it is possible that I level out here. Where does that look like? 1, 2, 3, about 3.5. That's fine. It may be that my sequence levels out close to where I hit 7, right? But the point is, no matter what it looks like, if it is bounded and monotonic, then we have to level off. And therefore, since we have to level off, I have to have a limit. Now again, notice that the upper limit here, the green sequence appears to have upper limit 7. The red sequence appears to be going closer to 3.5, but it can be anything. But bounded monotonic sequences have to converge. Now again, that's a nice fact to know, but usually when we're finding limits, we actually use the techniques that we know from before. All right, so here's what we're going to do. We're going to take a look at these 3 sequences, okay, where the nth term is 4 minus 1 over n, the nth term is 3n over n plus 2, and the nth term is cosine n over n. And we're going to determine if the sequence is bounded, if it's monotonic, and then we're going to find the limits. Okay? If you want to, you can pause the video right now and then try to find the limit of each of these sequences and then see if it's bounded and monotonic just by using some common sense. So go ahead and pause the video. I'll give you about 5 seconds and then I'll come back and explain. All right, so let's take a look at that first sequence. 4 minus 1 over n is the nth term. So if I take the limit of the nth term, hopefully we've done this, or hopefully you know enough about limits to realize that that limit can be broken up into the limit of 4 minus the limit of 1 over n. And limit of 4 is just 4. Limit of 1 over n is just 0. So that sequence converges to 4. All right, so the limit of that sequence is 4. That sequence converges to 4. As far as the bounded and monotonic goes, this one is bounded. And if you think about it, this is always 4 minus a number. So the upper bound of that would be 4. You can never actually get anything that's above 4. Now the lower bound, well, this number 1 over n, when you plug in positive integers, 1 over n can be 1, it could be 1/2, it could be 1/3. Basically, the biggest it could be is 1. And so the lower bound is 3. All right? So every number here is between 4 and 3. So it is bounded, and by the way, it is also monotonic. And the easy way to see that, well, we could do it mathematically, but 4 minus 1, 4 minus a half, 4 minus a third, each number is continually increasing as n goes up. Okay, so it is monotonic, it is bounded, and it does have a real number limit. In this case, that real number limit is 4. Okay, most of the times, as far as the questions go on the test or anything like that, I'm just going to ask you for the limit and whether it converges or not. But it is a nice exercise to look and see if it's bounded, if it's not bounded, those types of things. Let's take a look at the next sequence here, 3n over n plus 2. Now, if you take the limit of 3n over n, crap, I hate when I do that. 3n, space there, over n plus 2. Well, you can either use L'Hopital's rule, or you can remember what we did in chapter 8, same size growth on top, same size growth on bottom. So just take the coefficients of 3 over 1. And we see that limit has the limit of the sequence is 3. So this one converges to 3. Now you may ask if this is like bounded, if this is, why am I not getting that? All right, bounded, if it's monotonic. It is in fact bounded. If you think about the smallest thing you can plug in, 1 and then 2 and then 3, list out the terms. It is bounded. When you plug in 1, you end up with 3 over 3. When you plug in 2, you end up with 6 over 4, and so on and so forth. What you'll see is it's increasing, so it is also monotonic because it is increasing. It is bounded, and the upper bound is, well, the upper bound is 3, lower bound is 1. You kind of have to list out some of the terms to actually see that. Again, I'm not going to list out the terms right now, but that's kind of how you'd see that. Upper bound is 3, lower bound is 1. Now this one's a little bit different. Cosine of n over n. If you take the limit of cosine, of n over n, dang it, I hate when I do that. Done that a number of times today. Thought I had a space there too. Cosine of n over n. That's not wanting me to do that. I apologize. I'm trying to type this in well so that I don't mess this up. Well, that didn't work very well. Okay, so we will try another technique. Holy smokes. Let me go through and push pause on this video for just a second. All right, now I've got it typed in right. So limit cosine n over n. Now, if you think about growth and comparing growth, this top cosine is a function that when you put anything into it is always between -1 and 1. And so it is always going to stay bounded between -1 and 1. N just keeps getting bigger and bigger and bigger. So this thing goes to 0 as n gets bigger and bigger and bigger. Right? We're going to have our numerator essentially staying the same, always between -1 and 1, and then our denominator grows to infinity. So we get 0. So this thing does converge. However, because of this top cosine, if you type in things like cosine of 1 and cosine of 2 and cosine of 3 and cosine of 4, what you'll see is it's not always going to be increasing or decreasing. In fact, once you get back to cosine of 5, cosine of 1 starts out as a positive number, 2, 3, and 4 are negative numbers. Cosine of 5 is back at a positive number. So this thing is not monotonic. There are times where cosine is positive and times where cosine is negative, so it kind of bounces back and forth because of that cosine. All right. It is bounded because technically it is, again, the numerator is always between -1 and 1, and the denominator is always, well, at most 1. So it's bounded between -1 and +1, has to be, but it's not monotonic. All right. So that is just a look at the limits, finding the limits of these sequences. Now, like I said, most times I'm not going to ask you for whether a sequence is bounded, whether it's monotonic. I'll just ask you to find the limits. So that's what I want you to do. Go back again. I want you to use whatever techniques that you can and find the limits of these three sequences. Excuse me. So find the limits of these three sequences. Push pause on the video and then go ahead and find those limits. All right, so here we go. Finding these limits. So limit as n goes to infinity of 2/3 to the nth power. Now this is one thing that you should know, that as n grows bigger and bigger, if our base is below 1 in terms of absolute value, then this function will get closer and closer and closer to 0. So 2/3 to the nth power goes to 0. Um, again, this is a what we call a geometric sequence with base of 2/3. And anytime, well, let's do the next one as well. In a similar way, this one, remember that sequence, that theorem we said earlier, which said if, yep, the limit of the sequence when I throw away the positive negative signs goes to 0, then the limit of the sequence with positive or negative signs also has to go to 0. This is the absolute value theorem. So if you do this and get 0, this negative is just going to change you're going to get the same thing, but with negatives and positives. I'm not saying that very clearly, but let me say it again just a moment. So if you look at this sequence here, we start out at 2/3 and then we go to 4/9. This sequence here, we'd start out at -2/3 and then we go to positive 4/9 and then we go back to -8/27. Here, again, we just keep positive, positive, positive. All right, hopefully that makes sense. So we are term-wise going 2/3, 4/9, 8/27, and then what's the next one? 16/81. So that's that sequence there, the first few terms. First few terms of this sequence would be negative 2/3 and then a positive 4/9 and then a negative 8/27 and then a positive 16/81. And then the next term would be the negative of what we got up here. So again, all we're doing is we're throwing on some negative signs onto every other term of this sequence, of our first sequence here. And if our first sequence, the one that doesn't have any negative signs, goes to 0, then this second sequence, the one where we do the same except we throw on some negative signs, also has to go to 0 because of that absolute value theorem. All right, so by the way, these are both geometric sequences, and you should know that if you have a sequence and it is geometric, meaning it is some base to the nth power. Whoops, I should have scrolled up there. Let's call that base R for some strange reason that we'll use later. So if I have a sequence and it is some value R to the nth power, then the limit of that sequence of R to the nth power is 0 if R is between -1 and 1. So if R is between -1 and 1, then the limit is 0. And if R is bigger than 1, then this thing goes to infinity. All right, and we've seen that before. 2 to the nth power just grows and grows and grows and grows. If R equals 1, then obviously the sequence goes to 1. It's always just constant 1. So there you go. Lift the limit. If R is between -1 and 1, then we get 0. If R is bigger than 1, then it goes to infinity. By the way, if it's less than -1, then the limit doesn't exist. It bounces back and forth. All right, last problem here in this section. That was a little bit longer than I expected, so not a big deal. All right, so we're taking the limit of 5n e to the negative n. 5n e to the negative n. This one's going to be one of those ones that's easier to rewrite and see. Whoops. I apologize. I thought I didn't do that. So it's a lot easier to see this if we call this 5n divided by e to the n. Did it again. All right. 5n e to the n. There you go. And you can do this one of two ways. You can do L'Hopital's rule, infinity over infinity, so you could take derivatives, or you could realize, oh, this is an exponential function. This base e is, remember, about 2.7-ish. And so this is a base that's bigger than 1. This exponential function is going to grow faster than this polynomial type function. And so it's going to look like the top stays still. The bottom gets really, really, really big. So that limit has to be 0. Okay? So this sequence converges to 0. All right. So again, what to take away from this chapter, this section, I should say. this section, first off, we have to understand what limits do, the various ways that we can write limits, either by their terms or listing them off as a function of the nth term, listing them off recursively. We need to know how to go back and forth between the terms and the recursive and the function and the terms and so on and so forth. And then understand how to get limits of sequences. Remember, limits of sequences are just limits of the functions. There's a couple of rules here, the absolute value theorem, the squeeze theorem, and the monotonic, bounded monotonic sequence theorem that the book devotes a lot of time to. Again, they're pretty common sense type theorems once you think about them, but they're not something that we're going to use an awful lot. What techniques we're going to use are the observances that you've hopefully learned in Calc 1 and that we saw in the last chapter. So that is it for section 9.1. All right.